the iconic image of faraway galaxies and one of the most observed regions of space, has just received a spectroscopic upgrade. Hubble Ultra Deep Field, that iconic image peppered with faraway galaxies, just got a whole lot deeper. The tiny square in fornax that the Hubble Space Telescope stared at for almost 12 days in 2003 became the sharpest, most sensitively recorded region of the sky. Now, the multi-unit spectroscopic explorer MUSE on the European Southern Observatory's very large telescope in Chile has taken the image one step further. MUSE's observations of the 10-square arc-minute field revealed 162 objects not detected by Hubble, including 72 new distant galaxies. Not only that, but the instrument sharpened our measurements of all the galaxies' distances. 10 papers in a special issue of Astronomy Astrophysics reveal the implications for the formation and evolution of stars and galaxies across cosmic time. This image shows the Hubble Ultra Deep Field region, a tiny but much-studied region in the constellation of Fornax, as observed with the MUSE instrument on ESO's Very Large Telescope. But this picture only gives a very partial view of the riches of the MUSE data, which also provide a spectrum for each pixel in the picture. ESO MUSE HUDF collaboration spectroscopic upgrade. If a picture is worth 1,000 words, then a spectrum is worth 1,000 pictures. Splitting a galaxy's light into its component colors reveals the motions within the stars it bears, and, most importantly, especially for cosmologists, the galaxy's exact distance. Over the years, follow-up observations with ground and space-based telescopes have expanded the Hubble Ultra Deep Field HUDF to many other wavelengths, including radio, infrared, near-infrared, ultraviolet, and X-rays. Astronomers have used this multi-wavelength abundance to estimate the redshifts, and hence the distances, of 9,927 galaxies. The youngest of these live in a universe just 600 million years old. But these redshifts were not exact measurements that would require a spectrum for each galaxy, and spectroscopic follow-up is difficult when the targets are thousands of faint galaxies overlapping in a tiny region of sky. So astronomers have largely gauged distances by comparing galaxies' brightness in broad wavelength bands to the brightness expected from typical galaxies at the distance. Such estimates, known as photometric redshifts, aren't precise enough to see if two galaxies lie close to each other in space, for example. MUSE allowed a different approach. Rather than take one spectrum at a time, Roland Bacon-Lyon Center for Astrophysics Research, France led the MUSE HUDF survey team in taking everything's spectrum, all at once. Known as integral field spectroscopy, this technique produces a three-dimensional data cube by measuring a spectrum for every single pixel in an image. After 137 hours on the telescope, MUSE had increased the number of galaxies with spectroscopic redshifts nearly an order of magnitude, from 161 to 1,338 galaxies. These precise distances will have reverberations throughout the fields of star formation and galaxy evolution. Emi Vento, University of Toulouse, France, and colleagues, for example, used this data to identify 113 close pairs of galaxies distributed across 12 billion years of cosmic time. They show that the rate at which galaxies merge increases until roughly 2 billion years after the Big Bang, after which it subsides, a pattern that echoes the peak of star formation in the early universe. The authors plan to study the connection between merger rate and star formation in future studies. Finding galactic dust bunnies. MUSE also enabled astronomers to find galaxies that had evaded previous detection. Faint, low-mass galaxies pervade the early universe like so many dust bunnies, but even though they're teeming with newborn stars, they emit most of the radiation at a single wavelength, known as Lyman alpha. Hubble's direct imaging missed many of these objects. MUSE caught 604 of them, including 72 new ones that Hubble had not detected, because astronomers were able to slice apart the data cube, searching the HUDF specifically for strong Lyman alpha emitters. As Alyssa Drake-Lyon Center for Astrophysics Research, France, and colleagues show, these diminutive galaxies had an important role to play They could have single-handedly lit up the young universe during what is known as the epoch of reionization. Astronomers are also using the MUSE observations to investigate hydrogen-rich gas halos around faraway galaxies, galaxy-scale winds, and the connection to star formation and rotational velocity curves of even very distant galaxies. This composite shows the Hubble ultra-deep field region and highlights in blue the glowing halos of gas around many distant galaxies. So MUSE HUDFD. You can explore more of the results in the following papers. Links here are to the preprints of the articles published in Astronomy Astrophysics.